Okay, so today we start the first of two lectures that are dealing with multivariate clustering. So we're moving away from the single variable to multiple variables. Today is not going to be that spatial. There's a little part to it that I call spatializing these kinds of analysis, but this is pretty standard multivariate analysis. Some of you may have had this before, but I'd like to go over it. This day and age in the machine learning world, this is called, when I grew up, it was called cluster analysis. It's exactly the same thing. So this hasn't changed. It's been around for a long time, and it's very powerful. So what I want to do today is kind of start us off, talk about the problem that we encounter moving from one variable or even two variables to many variables, 20, 100, thousands in the big data world and in the bioinformatics world. And then cover two very commonly used but also very useful techniques of dimension reduction. So basically the challenge is with multiple dimensions, there's too many dimensions, it's hard to do the analyses, it's hard to interpret, it's hard to visualize. So let's make it simpler. Let's reduce it to something that we can handle, 2 dimensions, etc. So principal components, very powerful technique with many, many different applications, and then multidimensional scaling, which is a slightly different take on it. And then I'll close with two basic, or as I call them, classic clustering methods, k-means clustering and hierarchical. Now, today won't really deal with them, but next week we'll look at what happens when you multivariate aspect of the clustering with the spatial aspect. And this goes back to our early discussion of spatial autocorrelation. Spatial autocorrelation was about combining attribute similarity and locational similarity. And so next week we'll make that explicit in the clustering world. And you'll see in the second half of the discussion what I mean by that. So what is the problem? And this problem is referred to as the curse of dimensionality, and it is a real curse. It's basically means that you can't just automatically scale up. So whatever works for 1 or 2 dimensions doesn't necessarily work in 20, 40, 100 dimensions. So low dimensional techniques break down in high dimensions, or, which is another aspect of the same thing, that the complexity of some operations, of some functions, increases exponentially with the variable dimension. So what that means, the key concept in that is that it's more than linear. As long as it's linear, you can keep up. So if you have 2 dimensions and it's twice as hard, fine. But if it's 2 dimensions and it's 10 times as hard, and then 3 dimensions, it's 1,000 times as hard, then you're in trouble, right? And that's what happens in multidimensional analysis, multivariate analysis. And there are 2 examples that I like to use, and I have a third one that I'll talk about in a few minutes, that come out of this book on the elements of statistical learning, which if you're into some technical aspects of this, I highly recommend. It's very good math and stats background, but if you have that, it's really very interesting because it provides kind of a different perspective on all the data science buzz and the machine learning buzz from a rigorous statistical perspective. So the first example that I took out of this book by Hastie, Tibshirani, and Friedman is that what happens, in other words, how far do you have to go to capture a certain percentage of the data dimension as the number of variables goes up. So assume a uniformly distributed variable on a line, right? So how far do you have to go on average to find 10% of the data? That's 10% of the line, right? How far do you have to go to have 20% of the data, 25% of the line? So I don't have my thing. So the bottom line, the straight line, is for one dimension, and it's just linear. So if you want more percent of the data, you have to go further, right? Now, once you go to 2 dimensions, you see that curve, it curves up. So 2 dimensions, if you want 10%, you have to get close to 30% of the data cube. So think of this data cube on the left. So we did this when we had the 3D visualization and the 3D scatter with the little red box that was moving around. And if you remember, you may not have thought at that time, but these points floating in the 3-dimensional box were very far apart, rather as compared to, say, a 2-dimensional scatter plot where they were relatively close. So the point of this is, if you are in 3 dimensions and you want to capture 10% of the data, you have to go to close to half the size of the box. And that's something that is going to completely throw you out if you have to deal with 10 dimensions or more, because then you have to basically cover the whole thing to get even a very small fraction of the data, because in multiple dimensions, in some sense, this is not completely correct, but maybe you can visualize it, they're further apart. They're floating around. So the same 85 points are now floating around in 3 dimensions, 5 dimensions, 6 dimensions. So there's more space to be crossed to get the same amount of information. So if you want to capture just 1/10 of the data, say to do a cross-validation, you have to basically look around in 90% of the data cube, which is very inefficient. So that's why it's called a curse, because it makes your life really difficult. Another one similar is how far do you have to go to get, on average again, the first nearest neighbor. So this is a very powerful concept in searching, data machine learning, is finding the observation that is closest to you. So in 1 dimension, that's shown by the orange vertical bar, and again, this is uniformly distributed points. In 1 dimension, you don't have to go very far. In 2 dimensions, you have to go more than double already. And so in multiple dimensions, and multiple doesn't have to be that large, you have to go way too far to get your first nearest neighbor. So K and N, which we to get spatial weights, for example, K nearest neighbors, in 2 dimensions, it was very scalable, very easy to do. K and N in 20 dimensions, forget it, because they're too far. It's not an efficient technique to use. So basically, this is a technique, K nearest neighbors, very intuitive, very powerful in small dimensions, but forget it in large dimensions. So then you have to think about tricks of how to get the same result without using the same technique. And then the third one that I thought of just the other day is in the context of simulations, if you have to draw parameters from a parameter space. So this is also in optimization. If you want to find the maximum of a function of 1 parameter, and you know the parameter is between 0 and 1, you can just basically take 10 values on the line and compute the function and just graph it, right? So getting a sample of the values from that 1 interval is pretty straightforward. In 2 dimensions, it's already much because you have to combine, and then it's impossible to get a nice dimension. So that's a real, again, a curse of dimensionality, in that you cannot really scale this up to higher dimensions. So this is something to keep in mind, and we don't really think about this naturally because we're kind of trained in a 1-dimensional world, or at most a 2-dimensional world, correlations, scatter plots, linear regressions. But in a multidimensional world, a lot of the things that we take for granted just simply don't work. So we have to do something different. And the one thing that we can do is dimension reduction. In other words, cheating, right? So we're going back to what we know, 2 dimensions, 1 dimension, 3 dimensions maybe, by creating new variables that replace the original variables. So say we start with 20 variables. And there's no way we can do a 20-dimensional scatter plot. So we try to find a smaller, much smaller number of new variables that capture as much of the information in the original variables as possible. And so what do we mean by information? Typically we mean the variance. So the principal components are a small number of variables that capture as much of the variance in the original variables as possible in some quantifiable sense that I'll get to in a few minutes. So that's one approach. So instead of working with the 20 variables, we create 3, 4 new ones that we call principal components, and we work with those instead. In many ways, that is the approach. For example, a lot of face recognition software reduces hundreds of characteristics of a face to a much smaller number of principal components that you can then quickly categorize and analyze and use in a classification scheme to figure out whose face it is, for example. Another approach is to literally project down. So you project down in a lower dimension. We've already seen a very simple example of this. When we had our 3-dimensional scatter plot, we could, in GeoDa, project the cloud onto either one of the sides. So we went from 3 dimensions to 2 dimensions. And so this is kind of the same thing, but for many, many more dimensions. So you have high dimensional space, and one which I won't talk about today. But another approach is a little bit different, and it says, okay, what are the distances between these points being observations in multidimensional space? So think of the example. In our 3D scatter plot, we could see the points in there, and you can compute the distance between these points in multi-attribute space. So given that distance, what are the coordinates in 2-dimensional space that respect this distance the most? This is a classic projection problem. You know, I haven't talked about the mathematics of projection, but that's exactly what it is. So you have points on a 3-dimensional object, a sphere or some ellipsoid or something similar. So how can we represent these points on a lower dimensional object, a 2D map, so that their characteristics are respected as much as possible? One of these characteristics being the distance between the points. And so this then becomes an optimization problem where we try to find a solution to the coordinates in a fake artificial 2-dimensional space that reflect the distances between the points in a high-dimensional attribute space, a high-dimensional variable space. So that's multidimensional scaling. So I'll illustrate these two. So principal components, I can't help it. I have to throw in a little bit of matrix algebra. It's basically, the idea is to capture the variance, that is, so the variability among a number of different variables, there's no other word, in a lower dimension. And the only way for this to be effective is that it's a much lower dimension. And unfortunately, the example that I'll continue to be using of these French departments, which was used to illustrate multivariate approaches, is really bad for this. Because as we'll see, and also in the lab, so there's 6 variables, and you basically need 5 principal components to explain 95% of the variance, which is like, why bother, right? But where this is powerful is that and this happens a lot, that 2 or 3 principal components of the variance. This is often the case when you have census variables. So income related, housing related, population, demographic related. These are all measuring typically a few lower dimensional, some people call them latent variables, although that's a different interpretation of this. What are some underlying common factors here? So that's what this is about. These principal components, they capture as much of the variance as possible. You can also think of them as the best linear fit of some surface to the cloud point in higher dimensions. So it's linear. There's also nonlinear principal components, but we won't go there. And they're constructed and to solve the problem, this is another maximization problem, you have to put some structure in it. One structure is that we make them orthogonal, which means that by construction they're not correlated. I'll show you in a few minutes. There's zero correlation between them because that's how they're made. And also there's a scaling issue, so they're basically not unique because you can multiply everything by a factor and you have the same result. So you scale them so that their coefficients are actually the sum of the square of the coefficients is constrained to be 1, but that's a technical detail. So this kind of picture, again from the same book, illustrates what's going on in 2 dimensions. So you have a cloud point in 2 dimensions, and you see the first line along the elongation of the cloud point captures most of the variability. So the variability is the highest in that particular dimension. So think of this cloud point and you could rotate it in your mind so that you get the biggest extension in one particular direction. That's the first principal component. And then the second one is orthogonal to that by design, so perpendicular. So the second one is there's much less variability in the second dimension. So just think of this extending to 3, 4, 5, 20 dimensions is the same principle. So then mathematically, what does this boil down to? A very simple linear function. So the x1 through xp are our original variables. The c is the new variable, the principal component, that is nothing but a linear average, a weighted sum of the original variables. So you have, 20 variables, you have these different a coefficients, and you construct a new one. And then this new one turns out to maybe explain half of the variance in your original variables. And then you do it again, make sure that the second one is orthogonal to this, perpendicular, and that one explains maybe 20% of the variance. So you're already at 70% of the variance with just 2 variables instead of 20 variables. That's really the power of this. So it's an optimization problem, and for it to give you a unique solution, there isn't a unique solution, but to avoid arbitrariness, we scale the coefficients so that their sums equal 1. And basically, each of these principal components gives you the direction of the greatest variability, greatest variation. And you can also think of it as the closest linear fit to the points as a cloud. Here's the matrix algebra. If you've never heard of this, don't worry about it. Just believe me that it works, okay? So the idea is, what are these principal components and how do we get them? And as it turns out, the principal components are simply, as I said, a weighted sum of the original variables. So they involve the original variables, the x. So the question is, what are these coefficients? It turns out these coefficients are the values for the eigenvectors of the cross product matrix. So if you have the matrix of observations as x, then you do in matrix algebra x prime x. So x prime is a transpose. So if x is of dimension n by p, n observations, p variables, then the flip, the transpose, is p by n. And so the product of these two, p by n, n by p, is a p by p variable, p by p matrix. P is good, that's small. N is not good, that's large, right? So this works for as big a data. It's not n that matters, it's p that matters, the number of variables. So as it turns out, there is such a thing called the eigen decomposition of a square matrix. So the eigenvalues and eigenvectors are really weird things, right? I found, and I've been at this for a while, that it's really hard to get an intuition for it. This is my best try, okay? So you may know that a multiplication of a matrix with a vector, square matrix with a vector, is nothing but a geometric manipulation. So think of a vector, in 3D as, say, a line with an arrow. They usually draw it with an arrow. So you have this line here, right? And so you want to rotate it, right? How do you do that? Mathematically, by pre-multiplying the vector that corresponds to that line with a matrix. And the numbers in the matrix determine how far you rotate. They also determine whether you just rotate or also extend. So you can take a vector, let's say, 2 feet, going in a 30-degree orientation, and you pre-multiply it by a matrix to make it a 4 feet vector in a 90-degree rotation. That's just how the geometry works. Well, eigenvectors and eigenvalues are this combination, they're tied together, they hang together, that makes sure that for that particular matrix, any transformation stays on the same line. So there is no effect of rotation. There's just a shift in length. And that's just a particular weird thing. You have a matrix. Typically a matrix both rotates and shifts. Well, for this particular vector and this particular coefficient, the eigenvalue, the rotation and shift is only a shift. Okay. It's weird, but that's my... As it turns out, these things are really, really important in characterizing the properties of matrices. And they come back in many, many statistical and optimization applications, including this one. So as it turns out, these principal components that we want are the coefficients of them are the solutions to the eigenvectors. And then the eigenvalues turn out to be the variances, the part of the variance of all the variables that is explained by each of these components. So each eigenvalue has an eigenvector. The eigenvector gives the coefficients to make the principal component. The eigenvalue gives how much of the original variance is explained by that component. So that's how it all hangs together. So then mathematically, this is just how you do it. You take this matrix and you get the eigenvectors and the eigenvalues. In my day, you had to do this by hand. Now you don't. You just say eigen and there it is. But there's a lot going on to do this for larger or ill-behaved matrices. One thing to remember about eigenvalues, they do not scale. So after about couple of thousand, the properties are really bad. So this is a good thing applied to p by p because p tends to be much smaller than n. If you have to apply eigenvalues to n by n, you're in trouble with large data. So then there's another way to explain this, which as it turns out, we can skip a lot of the math. If you like the math, you can read it. So if we come back here to x prime x, we can get there in another route, which turns out to be computationally more efficient, which is called the singular value decomposition. Singular value decomposition is a little bit more complicated than a simple, quote unquote, eigenvalue decomposition. But at the end of the day, for this particular problem, it's basically the same structure. You recognize the v. This is the same eigenvector. Now we have d squared, so the eigenvalues are the square of the diagonal, singular values. So that's the relation between the two. But other than that, everything is the same. So that's the mathematical background. That's how you get the solution, right? Believe me, it works, right? So once you have them, you can construct these things. So you have the solutions for the eigenvector, you have your original variables, you multiply it by the coefficients, and you're in business. One thing to keep in mind is that these, and I already mentioned there's a certain arbitrariness in the solutions, and one that often throws people who do this for the first time for a loop is that the signs do not matter. You can flip all the signs of the coefficients, all of them, not just one, all of them together, and it's the same solution. So some software, or depending on which method you use, for example, computationally, you can get the principal components either by doing the eigenvalue decomposition, that's the old way, or by doing the singular value decomposition and then get the eigenvalues from that. That's the new way. And depending on which approach is used in the software and which convention is used, you can get results with opposite signs. And the first time you see this, you might say, what's going on here? Very choice of the software, whether it picks one sign or another sign. The squares of the coefficients have to add up to 1. So if they don't, then it is a mistake, right? So that's just a little formalism. What do we really want from these? We want to, a couple of things. So we want to find out how are these components constructed? How are they made up? Which of the original variables contribute to them? So ideally, for interpretation purposes, let me give an artificial example. Let's say you have a whole bunch of census variables. A bunch of them pertain to race and ethnicity. A bunch of them pertain to income, and a bunch of them pertain to education. So you throw all these variables in your principal component. You get a first principal component with all coefficients for ethnicity and race, and then 0 for all the other ones. So then you can interpret this first component as ethnicity or race. Would you ever be so lucky? In my experience, you need a lot of imagination to interpret the components. If you're lucky, it's nice and orthogonal. Mostly, it's a little messier, and you kind of have to force yourself to interpret the loadings, as they're called. But this is a primary interest. So what do these components represent in terms of the underlying variables? How do they map from the underlying variables to the new variables? Then the other thing which is very practical, very needed, is the new variable itself, the principal component. So you take your original variables, you multiply them by these c's, and you get a new variable which you can then use in analysis. For example, a common quote-unquote solution to multicollinearity. I'm assuming you're familiar with multicollinearity. If you run a regression and your explanatory variables are highly correlated, things will be very messy. So a solution to this is to replace all your highly correlated variables by a few principal components, because the principal components are not correlated by construction. So you don't have a multicollinearity problem. You cannot, right? The problem then, of course, is how do you interpret the results? Because the results are really the coefficients of the principal components, which are in effect the coefficients of the principal components, times the coefficients of the loadings, times the original variables. So a variable is going to be part of the first component, but also part of the second component, and also part of the third component. So the interpretation may be a little different. But this is the power of dimension reduction, right? This is why we do this. We have our original set of variables. It's too much. We reduce it to a small number of new variables, our principal components. And then as a diagnostic, we want to know how well this works and how much of the original variability in our original variables is actually explained by these new much smaller set of variables. What is the proportion of the variance that is explained? So let's roll the dice. We're going to use the same data set. I've already talked about this. We have these 6 variables. I mentioned the variables are weird. They're all flipped around so that more is better. So it's a crime rate. Typically, a higher crime rate is worse. But it's not crime over people, it's people over crime. So a higher number is actually fewer crimes. So as long as you know that, it's you can understand it. These variables have very different distributions spatially. If you just quickly glance, you know, the dark parts are in different parts of the country for different variables, so they don't actually line up very well. And that is confirmed by the correlation matrix. If you look at these correlations, they're pretty bad. You know, like the largest one is 0.41, and then there's several 0.02, 0.1, 0.08. So there isn't a lot of intercorrelation. So I'm surprised this was used as an example to illustrate multivariate analysis, but because it's really lousy for that. You want to see strong intercorrelation. Then it makes sense to reduce your variables by smaller number of variables. And we'll see in a second that this is actually the case here. So this is, so you don't have this yet. I'm hoping to get it to you by the weekend, but GeoDa now does all this stuff and gives you all these summary characteristics. And now they are correct. In the earlier version, there were some weird things that we fixed. So this is the kind of result that you get. So let's start with the eigenvalues. So these are this is a 6 by 6, you know, our x prime x matrix is 6 by 6. So we'll have 6 eigenvalues and then 6 vectors with 6 elements each, and these 6 elements will be the coefficients that we multiply the original variables by. So the eigenvalues are the variances, and the standard deviations are the square root of the variances. So if you look at the top line and you have a calculator handy, you take the square root of 2.14047, and that's 1.46, etc. And you do this for all of them, it's exactly the same thing. So this is, in a sense, kind of the magic of these eigenvalues. They turn out to be the variance explained. You don't have to do anything special. And then we can, of course, figure out how much of the total variance is explained by each of these principal components. So again, take your calculator, add up these 6 numbers. That is the total variance, about 6. Now, think about it. These variables are all standardized so that their mean is 0 and their variance is 1. So what is the total variance? 6. There's 6 variables. So then each of these eigenvalues is the variance corresponding to one of the principal components. So you take the ratio of the first variance over the total variance, and that gives the percentage explained. And then we can make it cumulative, and we see how many principal components do we need to explain X% of the original variables. And as I mentioned before, typically by the time you're at the third one, you're up to 90% of the variance explained. In this particular example, as I said, is really lousy. You have to go up to 5 principal components to explain 95% of the original variables. That sort of defeats the purpose. The whole purpose is dimension reduction. Going from 6 to 5 is not exactly dimension reduction. But you know, if we look at 2 of them, we're over half. And for our purposes, that's what we're going to be doing. So this is the main output of a principal component analysis. It gives you a sense of how well you do in terms of explaining the original variance. And it gives you the specific variances associated with each of the components. So then, how many of these components should we use? And I give you an example. I mean, there is no hard and fast rules. There are a lot of ad hoc rules. And we've seen this before, but I can't remember in what context. But this is called the scree plot. This is basically a plot of simply the number of components on the horizontal axis, and then the proportion or the fraction of the variance that explained. So on the left hand is something that you'd like to see, with what is called an elbow in the curve or a kink in the curve. So you get a very steep decline and then it flattens out. So basically where it flattens out, you stop, because the gain from adding additional components is marginal, right? In our example, unfortunately, there's no such thing. I mean, it takes a lot of imagination to find a kink in that plot. It's called a scree plot. Okay, so basically we take this information here from the second line and we put that in a plot. That is the scree plot, or we take the cumulative one, and that's just a complement of this the other way around. So the cumulative one goes up, and again, the scales could be changed, but what you want to see is some kind of bend in the curve, and in our example, we don't really see that. So the scree plot is a standard diagnostic graphic to figure out how many principal components you should need. Now, I know where else I have the scree plot, and it's coming up. I thought it came, but it's not. It's coming up. We'll see it again when we look at the clustering later on. Okay, so then how do we actually get these principal components? So these columns are nothing but the eigenvectors. So if you've never seen an eigenvector before, this is an eigenvector, one for each principal component. And they're scaled such that the sum of squares, and so the squares are here for the first principal component, they add up to 1. So that makes them unique. Otherwise, if you multiply both sides by the same constant, the equality remains. So there is that kind of arbitrariness that we get rid of by scaling the coefficients. So these, if you multiply the first variable by this coefficient, and then the second variable by the second coefficient, and add it all up, that gives you a new number which corresponds to your new variable, your first principal component. That's how it works. And then the last thing we can do is figure out, I mean, you might think that by looking at these coefficients, you can figure out what is the contribution of each dimension to the principal component. And you sort of can, but it's much better to compute the actual correlation between the original variable and the new variable, the principal component. And you don't have to square it, but if you square it, then if you go along the row, you see what percentage of the variance of the original variable, so the variable on the left-hand side, is explained by each of the components. So if we look at the top line, crime against persons, we see that the first component has very little to do with that. But the second component and the third component load very heavily. So between the second and the third component, we have close to 90% of the variability in crime against persons. Crime against property is 56% by the first component. So this is how you interpret these components. So what you would say is, by looking at PC1 going down now, we see that it's heavily correlated with sides, whereas the second one is heavily loaded on crime against persons and donations. Now, one way to visualize this is called a biplot. And a biplot just shows in 2 dimensions what I briefly described. So a biplot, if you look at these little lines with arrows, those are vectors. They show you how each component is represented by different variables. So the ones that go far up deal with the component. So what do we see here? High arrows up for donations and crime against persons, and we go back here, and we look at the correlations on the second PC2, crime against persons and donations, very high. And then for the other ones, we see a long dimension on the first component, and they correspond with high correlations in PC1, in the PC1 column. Okay. This is a biplot. This is used to visually explain. Of course, you can only do this for 2 components at a time, but you can do them pairwise, 1 against 2, 2 against 3, and so on. Basically, all they do is give you the information that's already here. So this tells you how each component is correlated with the original variables. Then I promise this, they are uncorrelated. So if you do a scatter plot of one component, the first component against the second component, the slope of the linear fit is 0. Set it up that way. Okay. So if you want, like in a multicollinearity problem, you want 2 variables that are totally uncorrelated, principal components is your solution. So that's one approach, and it's non-spatial, but how can we spatialize this? That's what I like to do. And of course, nothing keeps you from making maps of the spatial distribution of the principal components, or to find local clusters in the spatial distribution of components, which is another way of thinking about multivariate local clusters. So I think I talked a little bit about the multivariate local geary, where you have multiple variables and you try to find their local clusters. Instead of going that route, because we're fighting the curse of dimensionality, you say, no, let's just look at the first or the second principal component and see if we can find clusters in those spatially. Because if we go back here, we know what this means. We know that if the first principal component clusters very heavily in space, that in fact this implies that the variables that load very heavily on this principal component cluster together in space. So that's another way of thinking about multivariate spatial correlation. And the more I think about it, once you get to many variables, it is the only way to go, because you get killed by this curse of dimensionality. And so you can do bivariate. The thing about the bivariate local correlation, but also the bivariate global correlation, is that you don't have to worry about the in situ correlation of these variables. Remember when I discussed bivariate, I think maybe I didn't discuss it, but it's in the notes. When you have bivariate spatial correlation, that's a very difficult concept, because you're confusing the correlation between the variables themselves in place with the correlation between the variables and the other variable in neighboring locations. But with principal components, you don't have to worry about that, because they're uncorrelated. So the only correlation you're picking up is between the neighbors. There is no correlation in the location itself, which is a clear advantage of this. Okay, multidimensional scaling. Different idea. We think again of our point cloud. We compute distances in Euclidean distances in p dimensions, and then we try to match these distances in some sense to coordinates in 2 dimensions that are as close as possible to these distances. So it's an optimization problem. We have dij, which is the distance in p dimensions, where p can be as large as it can be, because all it is a sum of square deviations. So it's very easy to compute. But then given that distance, the dij, in p dimensions, are coordinates in 2 dimensions, zi and zj, that gives us a solution to this problem. And this problem is minimize the discrepancy between this distance measure, which is from p dimensions, and this distance measure, which is from 2 dimensions. Right? And so this is a nonlinear optimization problem, and the result of this is a set of coordinates in 2 dimensions. So this is called a multidimensional scaling plot. These V1 and V2 are these solutions to that optimization problem, right? And again, depending on how you do this, because this also uses eigenvalues, but I won't get into this. I think I got my quota for today in terms of eigenvalues. But the signs can be flipped. So what is V1 and V2 in one software can be V2 and V1 in another. So the axes is not what matters, it's the distances that matter. So the distances between these points mimic the distances in multidimensional space. And so then again, we can spatialize this, and this is really cool. You can see if observations that are close in multi-attribute space, which are points that are close together in the multidimensional scaling plot, where are they on the map? Are they neighbors? Are they not neighbors? And of course, you can flip it around, and you can look on the map where are these neighbors in terms of their multi-attribute closeness. So this is another way of thinking about the tension between attribute similarity, which is depicted in the multidimensional scaling map, and geographic similarity, which is depicted in our geographical map. Okay, so that's a different way of thinking about this. Of course, you cannot do local clusters or anything with these multidimensional scaling. They're already a summary of the similarity in high dimensional space. But you can look at them on a map and do some other cool things that I don't really have time to talk about, because I want to talk about 2 kind of mainstays of cluster analysis, which is now called unsupervised learning, but it's the same. So this is a grouping problem. So again, it's typically a problem when you have a lot of data, a lot of information. So you can think of this in marketing. You have a bunch of different products. You only have a marketing budget that you can have 5 campaigns. How do you group your products into 5 groups where the products are as similar as possible, so that each of these clusters then gets a given marketing campaign? Okay? Or given, there's some examples in bioinformatics. I'm not an expert on genes and markers and all that stuff. You have thousands of these markers. You have thousands of patients. Is there any way that you can group them by means of specific characteristics of these markers? So then people who, are in one category tend to have this disease, or people in another category tend to not have any disease. That's the kind of way in which this is being used today, primarily to trawl really large volumes of data and try to find in the data. And the principle is very simple. So we have a measure of dissimilarity, say square distance. And we're grouping observations which have multiple attributes into subsets of the data. And within each subset, you boundaries between the subsets. So you want the between variability or between dissimilarity to be high. You want the within very similar inside a group, everybody looks alike, but between groups look very different. That's what you want. And each observation, at least in classic clustering, there's also fuzzy clustering, but in classic clustering, you're in one group and only one group. In fuzzy clustering or in probabilistic clustering, there is a probability that you belong to one group versus another group, and it's not one or nothing, right? So lots of different things to think about. how are we going to measure similarity? I mentioned Euclidean distance, but that's by no means the only thing. You can also take absolute distance. The advantages to Euclidean distance is that they easily mathematically reduce to square deviations from the mean, which is easy to compute. When you have absolute differences, then you have to figure out medians, which is not that easy to do, but it can be done. You can use correlations. You can use rank correlations if your data are not continuous but ordinal, and so on. There's many, many different ways, as long as it expresses a notion of dissimilarity or similarity. Another big issue, and we'll get into next week as well, is how many groups you should pick. You know, sometimes it's obvious, like, you know, in my marketing example, sometimes it's not so. You know, trawling through, you know, medical data, you don't necessarily know how many groups would be a good organization. And then this isn't easy to do. It's easy to do, it's easy to conceptualize. And it's easy to do on toy data sets. It doesn't scale well. It doesn't scale well. Just to give you an idea, with our 85 departments and we want 4 groups, we have this big number of possible arrangements. 10 to the 51st, that's a lot, 51 zeros after a 1. That's a big number, right? That's not something you can do exhaustively. Okay, some of the early problems were done exhaustively, but basically you can't do this. So you have to figure out an algorithm, which is a number of steps in a calculation, or a heuristic, which is the same thing. The difference between the two is that, well, they're basically the same thing, but a heuristic, you cannot prove that you actually have the optimal solution. You can often prove that you have a good solution, but you never know that you have the best solution. So there's a problem of what we call local optima. You know, if you can think of an optimization problem, you know, and think of a camel with 2 humps, and one is higher than the other one, you can get stuck on one and think you're in the optimum, but actually you need to be on the other one, right? And so that's a really vexing problem in any higher dimensional analysis, is that you basically can't tell whether you are in the global optimum or local optimum. The only way you can try to find out is if you approach the problem from a slightly different angle, do you end up with the same solution? And if you approach it from enough significantly different angles and still end up with the same solution, you can be fairly confident that it is a global optimum, but you can never be certain, right? So this similarity, we've seen this before. We saw it in the variogram. We saw it in Geary C. It's a square difference. That's the easiest case. Then the distance between 2 objects is just a higher dimensional generalization of this. So you sum the distance over j. J is the number of, j is the index of the different variables that are included in the observation. So an observation x is actually what we call a tuple, which is a multiple of observations on different variables. So if you have our 6 variables from the French example, each observation has 6 values, 1 for each variable. So then what is the distance between 2 observations? It's the distance between, for each of these variables, added up over all the dimensions. And then you can look at this as such, or you can look at it as a weighted average. Since and it's good practice to standardize the variables so that we, in a lot of multivariate analysis, you are going to get the effects of scale. And some variables are measured in thousands and others in tens. So you want to get rid of that, and you standardize everything so that it has a mean of 0 and a variance of 1. So then the weighting doesn't matter because they all have the same variance, so you don't have to worry about it. But in general, you should weigh these distance measures by something proportional to the inverse variance of the original variable. And it can make a difference, you know, and in some applications, it's actually not a good idea to standardize, but that's very application specific. So typically, we do standardized analysis. So as I said, many, many different ways to deal with this problem. Two canonical approaches. One is bottom-up, the one is top-down. So bottom-up is called hierarchical clustering. You basically group observations and you kind of climb up in a tree by grouping more and more, and then later you decide where to cut. And well, this results in a graphical representation which is called a dendrogram, and so then you decide where to cut in the dendrogram. And then the other way is to start with some random assignment of all observations to k groups and then improve your solution. So that's an optimization problem. You say, you know, just randomly assign each observation to one of 4 groups. Swap them out to see if you can do better in terms of our criterion in group similarity and between group dissimilarity. So let's say you have a grouping, you swap one observation from group 2 to group 1, and you see if it's better or worse. And if it's better, you keep it in group 1, and then you keep going. So the whole kind of mathematical problem is to come up with good heuristics, good algorithms to move from this initial random assignment to an assignment that is near optimal or hopefully optimal. So there's many different ways to do this. Let me start with hierarchical. So it literally is bottom up. So you take the 2 observations that are the closest and put them together. And I'll show you a graph in a second. And then once you have them together, you kind of have to recharacterize them. And that's the computational burden. How do you do that, right? Because rather than each being their own point, now they're being represented by some common point, because they are now treated as if there were one observation instead of 2 separate observations. So given that you figure out how to do that, and again, there's multiple ways to do that, then you find the next closest or the next 2 closest and then put them together. And so you climb up in the tree by putting everything together until everything is one cluster. So there's always 2 extremes. One extreme, if you have n observations, is that you have n clusters, right? We have 85 departments. We have 85 clusters. Each cluster is 1 observation. Right? Within group similarity, within group dissimilarity, 0, because there's only 1 observation. Between group dissimilarity, that's the total variance of the data set, right? At the other extreme, only 1 cluster, everything is in 1 cluster. Within group dissimilarity is the same as the total variance. Between group similarity, 0, because there's only 1 group, right? So everything in between is kind of a compromise between having every observation being by itself or putting them all together into 1 cluster. Right? So here's a picture out of one of my favorite books. This is Data Science in R. If you want to do serious data science in R, you should know this book backwards and forwards. It describes tidyverse, which is your major data wrangling tool in R. So we have our little points there in a scatter plot. It's 2 dimensions, so we can easily visualize this. And points 2 and 3 are the closest. So we eyeball this. Now, you would normally compute that. So then we start our little tree. We put 2 and 3 with a little connector between them. So that's the first step, the first level in the tree. Now, one thing to keep in mind is which one we call 2 or 3, or how we put them in the dendrogram is totally arbitrary. So never get hung up on the labeling in a dendrogram because it's arbitrary. You can switch things around. So then 2 are 5 and 7. So in the upper right graph, you see 5 and 7, and you see the little connector is 1 step higher. This is the second step in the process. So then we continue this and we add 1 to 2 and 3. So now we have this graph, and here you see again we're one step higher in the tree. And so we keep doing this, systematically adding observations, systematically adding steps in the tree until we're done. And then we define a cluster by cutting the tree horizontally. So wherever you cut, the number of branches that you end up with define the clusters. And the leaves, they're called at the bottom of the tree, are the elements in that cluster. So let's say I would cut, right above there would be 4 lines. Each of these lines, 8 would be by itself. The third one would be 5 and 7. The fourth one would be 4 by itself. And then the first one would be 2, 3, and 1. That's how the logic is. So it's a bottom-up process. You put observations that are close together in, you join them in the tree. The tree goes up in levels until you have them all joined. So as I mentioned, once you put 2 together, how do you characterize that new grouping of 2 observations? If you have two individual observations, it's easy to compute the difference between them. But if you put 2 together and then you have 1, how do you compute the difference? And there's many different ways. Complete linkage, as it's called, is when you take the furthest distance between the 2 groups. So you have 2 observations in one group and 3 in another. You take the ones from each group that are the furthest apart, and that is the dissimilarity between the 2 new groups. That's called complete linkage, and complete linkage tends to exact-looking clusters. Then the easiest solution is called single linkage, which takes the pair that is the closest together from each group. So that's the second graph. You see there's the smallest distance between the 2. Then average linkage takes all the pairwise distances and averages them out. So you can already imagine that computation-wise this is a pain in the neck, because you have to do all the squares of the observations in each group. And then the last one takes a midpoint and compute the distance between the midpoint. And you might think that's the most logical one, but again, computationally that's a pain because you have to compute the centroid each time, which is computationally heavy. So in practice, people tend to go between the complete and the linkage, and the complete gives much better results, as you see in a second. So this is an example of one of these dendrograms. It's not the example from the French. It's actually using Chicago community areas, but it gives you an idea of how this kind of climbs up by level, and then you cut to get the clusters. And as I said, we can now do this in GeoDa. GeoDa, for practical purposes, flips the hierarchy around, but it's the same thing. So these are the leaves, these 2 together, these together here, and so you build up the tree, and then you put the line in the tree. In this particular case, it gives you 5 clusters. These observations are in cluster 1, then those are in the next one. So you have these colors, and the colors are matched by a map. So if you do this in GeoDa, you get the map on the fly. If you do it in R, you have to go through some contortions to make the map, but it's basically the same thing. So then, what are we really looking for to characterize these clusters? As I said, there's many different ways of doing this. So the key is to really do sensitivity analysis and make sure that you can characterize these. So obviously we characterize them by this dissimilarity measure. So we have the total sum of squares, the variability in it. We have for each cluster the within sum of squares, and basically the difference between the sum of the individual within sum of squares and the total sum of squares is called the between sum of squares. So is maximize the between sum of squares relative to the total variance. So we make them as different as possible, or equivalently, would minimize the sum of the within sum of squares. So we make them within each other as similar as possible. So one very quick and dirty way to look at this is to look at the ratio of between sum of squares and total sum of squares. So this is what you get in GeoDa, hopefully by Monday. If not, we'll do it in R, or we'll do both. So you get the summary, you get some characteristics of how we did this. We used standardized variables, we used complete linkage, we used Euclidean distance. These are the centers of each cluster. So these are, in essence, the averages of the values for each variable that are part of that, for the observations that are part of that cluster. And then we have the breakdown of the total sum of squares to the variance within each of the clusters, and the ratio is 0.423, right? Complete linkage. Now we do it with 4, same thing, right? I don't have a lot of time, but you see with 4, it goes down to 0.33, and that's typical. I mean, as you have more clusters, the difference between them will get larger. So to some extent, to maximize the between cluster dissimilarity, you end up with each observation being its own cluster, which is the one extreme, right? But of course we don't want that. We want to group them, and then the key challenge will be to figure out where do we stop. You know, we go from 4 to 5 to 6 to 7 to 8, but where do we stop? This is single linkage. And single linkage tends to be characterized by really lousy solutions, in the sense that you get this. A few singletons and then everything else lumped into one big cluster. That's just the nature of the beast. This is a consequence of the criterion that you use. And we can see very quickly, if you just go down to the summary characteristic, this is pretty lousy compared to what we had before. Right? So single linkage is good for comparative purposes, but basically don't use it. K-means is another way to approach this. As I said, we start with a random assignment and then improve it. And we use heuristics to improve this. Again, in a nutshell, right? This is actually much more complicated than it's shown on this picture. But so you randomly assign 3 colors. Then you find the centroid in each of the colors. Those are the first set of crosses. Then you assign the closest points to each of the crosses. Now, it looks a little weird here. I don't know why they did this, but it doesn't look right. But just ignore that. You put the green points closest to the green cross, the blue points closest to the blue cross, and so on. Then you recompute the centroids of each of these groups, and you start all over until it converges. So you keep allocating. So obviously, element is where do you start with your first assignments. And each different assignment will end up with a different end solution. So what you want to do, and what typically every algorithm does, it does a whole bunch of these randomly and quickly compares them on this ratio, for example, then picks the best one. So you do 50 of these initial random assignments, pick the best one, and then start improving for that one. Critical for replication, you have to use the same random seed. If you don't use the same random seed, you're going to have a different solution every time, and it will be hugely confusing. I can guarantee that. But basically, conceptually, this is very easy, right? You start, you want 5 groups, okay, assign randomly to 5 groups, and then start improving. Computationally, it's not that simple. So in practice, how many groups? We have a criterion, we can compare them on the criterion, but where do we stop? Right? I mean, in the extreme, we end up with as many groups as observations, which kind of defeats the purpose, right? So where do we actually cut? This, as I mentioned, is sensitive to where you start. So typically you do many random assignments and then pick the best one. You have to do sensitivity analysis to make sure you're not stuck in a local optimum, and then if you want to have the same result each time, you have to control your random seeds. Just to illustrate this, this is what you get for, and then next week we'll look much more closely at the spatial distributions. But this is what you get with 4. So we have a bunch of summary there. Again, we have the cluster centers, the within cluster summa squared, the between cluster summa squared, and the ratio is 0.433, which is much better than what we had in the hierarchical clustering, as it happens in this case. But it's still not that great. I mean, typically, you want to be well over 50%. 0.43 is not that great. And then you can do this for 5, and you see it goes from 433 to 0.49. And I can't remember whether I have it in this class or in next week. Oh, I have something. So this is just summarizing these 3 complete linkage, hierarchical, single linkage, hierarchical, and k-means, all the ones with 4, k4. And as we saw in before, the worst one by far is single linkage, and then the k-means is a little better than complete linkage, which has more compact cluster in general. Okay, does this. So let me go back. Next week I'll talk about how you pick the k, and this is where I was running ahead. You use, again, a scree plot type of logic. So you have, let's say, the ratio of between summa squares and total summa squares for k, 2, 3, 4, 5, 6, and you look at the curve, and you want to find a point where the curve kind of shows an elbow, and then that's where you stop. And that's the k that you pick. But the moral of the story is sensitivity analysis, sensitivity analysis. And it gets even worse when we bring into space, which we'll do next week. So far, we haven't worried about whether these locations in clusters are geographically connected or not. In fact, they're not. Right? You see, the colors are arbitrary. The labeling is arbitrary. So 2 is not better than 1. They're categories. You can switch them around. In fact, we've already seen this in GeoDa, how you can do this. You can change the colors if you don't like them. So we see that some of these are more compact than others, but clearly, say the light green ones, there's 4 different separate parts. So there is no real geographical, similarity that matches the attribute similarity as obtained through this particular algorithm. Right. So then next week we'll be concerned with getting a compromise between these two, the tension between geographic similarity and attribute similarity. But the principles we covered today. So basically what we saw is once we go from 1 to 2 dimensions to multiple dimensions, we're basically in trouble. We have this curse of dimensionality. There's no way around it. So we make our life simpler. We reduce the dimensionality to a smaller number of variables, either using principal components or something similar, or projecting the points in 2 dimensions so that we can see how dissimilar they may be. And then we alternatively, so this is based on the variables. The second perspective is really focused on the observations. So we try to group the observations so that they are as similar as possible. So these could be, in this case they're departments, but they could be patients, they could be products in a marketing campaign, they could be identifiers of facial characteristics, they could be any number of things. They could be, there's some nice examples of using this in some of the machine learning books where they're used to identify letters, handwritten letters. So you have, a signature. How do you know that it's somebody's real signature? Or, post office. How did they read the zip code when it's written on an envelope, you know. They don't have somebody sitting there and this zip code and put them in a box. That's how they used to do it. Now it's all automatic. So what's going on there is something scans the whatever is written and then tries to figure out which numbers these are. And it figures that out. One of the ways in which this can be done is by just pixelizing the number and giving characteristics, and then, you know, depending on how many pixels you use, way too many. So then these are then reduced into principal components, 2, 3, 4, and it's amazing how much of the components can capture, and then you can use those in a classification. If you digitize this, classify, say it's a 6. No, it's a 3. That's how it works. So this stuff is actually used. This is becoming very, very critical in a big data world. Big data and big variable world. Okay, so in the lab, we'll hopefully use GeoDa to do this, but I also have some notebooks. It's a basic technique.